Hello. Okay. It's time. Where are we? Okay, let's get started. So, any question from last time? Okay. So last time we go through all our, let's see, 8 ROC properties. So basically, we think now we know ROC are straight strips in your complex plane, and they are basically bounded by the poles, at least for the rational functions which we focus on. So now if we have some algebraic expression of our Laplace transform, and there are multiple poles, and then we can write the poles on our complex plane, and then we can just read from the graph and see what are the possible ROCs. So there are 2 poles here, and they will cut the plane into 3 regions. And then found out there are 3 possible ROCs, the rightmost one, the middle one, and the leftmost one. And we know if the ROC is this rightmost one, then the function is going to be right-sided. And indeed, it corresponds to this right-sided function. Both of them have this u of t. And if the ROC is the leftmost part, then it's going to be the left-sided function. So it should be this minus t1. And if it's in the middle, then it's some weird 2-sided function. And also in this example, we see that sometimes the function just don't have a ROC. It corresponds to nothing. And we see this example once again when we do the inverse Fourier transform. We see that we can do partial fraction expansion to write your Laplace transform into those partial fractions, and then we do the inverse one by one, and they are corresponding to the first 2 examples we talked about. So it's either this right-sided function or this left-sided function. Okay. Yeah. And then when you do the inverse depends on which ROC you pick. And they look at the ROC and think about that when you are inverting each pole, which of the 2 choices makes sense. So if your ROC is the right side of most poles, then you need to pick the right side of those 2 ROC. And if your function is, okay, we don't have more picture. If the function is the left-sided, then you need to pick those 2 left-sided ROC. And if it's the middle part, then you need to pick 1 left and 1 right. Any question about the inverse Fourier transform? Oh, I guess I missed something. So the most theoretical thing that we want to use in the calculation, that is, where is it? Okay, yeah. So for general inverse Laplace transform, you can always calculate it as a Fourier transform of this xe to the minus sigma t. And also you can also think this more generally as the contouring integral inside the ROC. And you can basically pick any contour, but straight line are probably better. So you pick any any contour inside your ROC from negative infinity to positive infinity. Negative infinity imaginary to positive infinity imaginary, and you integrate along this line, and yeah, and that will give you the inverse Laplace transform. But yeah, but we probably won't have many examples of doing this. And to finish the inverse Laplace transform, we need to talk a little more about the partial fraction expansion. So this was usually in the inverse Fourier transform too, but we kind of skip it. So so the thing is, when you do the rational function and do partial fraction expansion, sometimes the numerator has more degree than the denominator, and when you do the division, you can get those remainder terms, so some polynomial left over. So the summation B something and S to a Q, and B not have constant term. Yeah, in that case, then you need to do the division first to get oh, that's not remainder, sorry. That's only HO quotient. Yeah. So anyway, you need to do the division first and get those terms, and then left with something you can actually do partial fraction expansion. And then when you do inverse Laplace transform, we look up table to do inverse Laplace transform for this thing. And we just tell you answer. So the first one is the constant term. And it's very similar to the, I think it's basically the same. The inverse Laplace transform of the constant term is basically the inverse Fourier transform of the constant term, which gives you this delta function. Okay. And now for those higher order polynomials, the inverse is also very similar to Fourier transform. You can use the differential formula, although we haven't talked about the differential formula, but it's going to be similar. Yeah. So you use the differential formula on this side, and you get extra s on this it should be you use the differential formula on the tan side, then you get extra s on the s side, and you work out everything. You find out that if you have s to the nth power as your Laplace transform, and when you do the inverse transform back, you get those u of n. And u of n are the things we talk about in chapter 2. They are the nth differential of delta of t. So just a reminder about what are the u of n. So we have u1 of t defined as the differential of delta of t. And they are really singular function. So the delta of t will kind of look like a very thin rectangular. And when you do the differential on it, then you get this weird two spike, positive spike, negative spike. So there are two spikes, so it's called doublet. And it can be used as some kind of representation of differentiation, because if you convolute it with another function, then I'll give you a differentiation of that function. And okay, so also some reminder we can skip. And you can generalize this to nth power, so you can have your u1 convolute with each other with itself, and you get the twice differentiation of delta of t. And when you convolute something with this u2, it gives you this second order differentiation, and you can do this k times, and it will be case order differentiation of delta, and you can convolute them with x and get case order differentiation of x of t. Okay, so those are what UKs are, and let's go back a little bit. So anyway, so you can do this, and you can do Laplace transform, and you can do inverse Laplace transform this to delta function, and those to all those u of n, and or you can be more general, you can think delta of t as u0 of n, u0 of t, sorry. Delta of t is also u0 of t, and so it just gives you a whole bunch of un here. And also I think other thing to say is those polynomials obviously don't have poles, so the RLC is everything, and so you don't need to think about the RLC. Okay. Any question about inverse Laplace transform of rational function? It's a pretty straightforward process. You do the division first, get those quotients, then do partial fraction expansion of the remainder. Then you look up table to do inverse Laplace transform, and you need to be careful about RLC. Okay, then let's go to the next thing. So this is, those slides are way longer than it should. And we are basically going to skip all the word, because if you just look at the equation and you look at the picture, it's pretty easy. Yeah, so it's, well, it's quite a simple concept here. So we are trying to get some qualitatives of the Fourier transform by looking at the pole-zero plot of the Laplace transform. But actually, this is something you can already do when you write down the Fourier transform. But anyway, but I guess it make more sense to think about poles when you are looking at the Laplace transform. Anyway, so Laplace transform is something we are thinking about rational functions. Okay, rational functions, so there are a whole bunch of zero, a whole bunch of poles. And so that's that. And now remember when you do Fourier transform, you are plugging j omega into this S. Okay, so maybe look at this picture. It's a little annoying. Okay, maybe this picture. Okay, so you might have some poles, and when you restrict back to the Fourier transform, then you are looking at basically looking at Laplace transform when your S is restricted to this axis. And now we have a rational function, right? So there are a whole bunch of those monomial terms. So it's going to be j omega minus beta and j omega minus alpha, those things. And this thing you can just apply basic complex number arithmetic to get a good estimate. So you can the thing we do is we think each of those terms in the polar form. So they're kind of a vector. How to say it? So yeah, I think the best way to see this, we think those as polar forms. So S minus beta or S minus alpha is going to be a complex number. And we can write this complex number as some magnitude times some phase vector that has a theta, right? Because it's a complex number, you can always write as a magnitude times the times the angle. And if you write the complex number in the polar form, then when you do multiplication, it's really easy to see what is the multiplication, because so you have complex number one and complex number two. You multiply together, then you see the magnitude multiplies together, and the angle will add together. And so you can, if you write all those in polar form, then the upper multiplication is easy to see what are qualitative. If some of them get large, then this thing will get large. And also the division is also easy, because when you get a division by a complex number, then the magnitude is going to get inverse. So it's going to from R1 to 1 over R1, and the angle is going to get a negative sign. So if you express all those monomial terms in the complex form, in the polar form, then you can basically read immediately what are the total complex, what are the magnitude and the angle of the total complex number. So the total magnitude is going to be all the r on the upper side divided by all the r on the lower side, and the theta is going to be the sum of all the theta on the upper side and subtract all the theta on the lower side. And you can also think of this as a vector. So the thing we just talked about. So you have some point S, and you have a pole or zero at A, right? Then that complex number S minus A can be seen as this vector. Okay, so this vector from A to S is the complex number S minus A. And then you can kind of visualize this R and theta from this picture. So R is going to be just the length of this vector. Okay. And the theta is the angle of this complex number, which is this angle, right? This angle theta here. Okay, so this is a basic geometric view of complex number. You can think a complex number as some kind of polar representation, and this magnitude r is the length of the vector. and the angle theta is, well, the theta counting from the positive real axis. So this is theta. Any question from the complex number? If not, then let's maybe go to example here. So example, so if you were your Laplace transform look like this. So 1 over s plus 1 over 2. So you have a pole at s equal to minus 1 over 2. And the region of convergence is is the right hand side. So it will contain the geometric axis. That's good. And then we can go back to the go back to the Fourier transform. So you restrict s back into j omega. Well, then just change s to j omega, and you get this Fourier transform. Then you can kind of qualitatively see the behavior of the thing by just looking at the complex plane. Right, so you have a pole at negative 1 over 2, and now you have this j omega plus 1 over 2 vector, which is basically this vector. So you from j omega, so this vector from minus 1 over 2 to j omega is the denominator of this thing. Okay? And now you can just look at the angle, and you can just look at the magnitude and the angle of this vector. So you see that the magnitude of this thing is going to be smallest when your omega is right here, right? Because that's closest to this pole. And so the magnitude is going to start from infinity when your omega is very negative, and then go again, going, and sorry, the magnitude is decreasing. Okay, so yeah, it's really annoying. Yeah, so this number is going to, magnitude of that number is going to be decreasing from when omega goes from infinity to 0, and the k is smallest, and then keep going, but you are 1 over the magnitude. So yeah, so 1 over the magnitude is going to be the smallest from here, then get the largest value here, and get smaller here. So that's how your do we have a picture? No, not quite. Okay, yeah, but so you can kind of get the feeling of the magnitude of your x of j omega. That is something that's start from 0 and grow, and then get biggest when omega is 0, then get smaller. And you can also see it algebraic here is 1 over omega squared plus 1 over 2 squared. So this is largest when omega equals 0. And you can also read the angle here. So the angle of this thing is going to start from, so when you go from negative infinity, so that the angle is negative pi over 2, and the angle to 0, and the angle to positive pi over 2. And you get negative sign, so actually from positive pi over 2 to negative pi over 2. And you can think about this function, that's fancy. So yeah, any question from this example? So we are basically, yeah, we are thinking about all the vectors from your pole zeros to the geometric axis, and we can get a qualitative description of how your Fourier transform will look like when your omega moves from here. And you just think about the length of those vectors and the angle of those vectors. Okay. And we get a more generalized example. Okay, so this is something actually talked more in chapter 6. Yeah, but so this is the first order system, which is the system that is described by this equation. And it's very nice because it's a fundamental, it's a system that occurs in nature quite a lot, and well, because it's a simple form, and also it's a building block for many engineering systems. And as you can probably guess, we also have second order system later, and but we won't go into too many detail here. We'll just give you a brief brief taste of those two systems. And if you want to know more details and the application plan, you can read chapter 6 of the book. But anyway, so that's the system, and we can calculate its Laplace transform, and it's going to be look like this. It's very similar to Fourier transform, and you can probably guess it's similar. So you will have differentiation property of the Laplace transform. So when you get a differentiation here, you get h twice. So that's why you get s tau here and the plus 1, and move things around, you get this h equal to over s tau plus 1. And we also calculate this in the chapter 6. So you have impulse response of the system look like this. And well, the real part is this because we are kind of assuming it's we are also using initial rest conditions, so the thing is causal. Okay. We'll see about that later. But anyway, so that's the Laplace transform, and that's the LC, and it's nicely contained in the so assuming tau is positive, and this contains the imaginary axis, so that's nice. And you can see this is really just a generalization of the previous example. So if you move things a little around here, you see that this term has a pole at -1 over tau, and this really behaves similarly to the previous example. So the magnitude of your Fourier transform is going to get a peak when omega equals 0, and it's going to 0 when your omega goes to plus infinity, negative infinity. And yeah, we can plot the you can plot the response here. So this is basically the magnitude of the response, but we're plotting in log plot for reasons that's more clear in chapter 6. But anyway, so you see this decaying behavior, and this can be kind of seen as the low pass filter, okay, because it's accepting it's passing at a low frequency and rejecting at a high frequency. And also this is kind of the cut in half of the previous plot we have for the frequency response. So the frequency, we are picking all the positive value because we are picking log plot, so you cannot really have the positive and negative. But anyway, so that's the frequency, the magnitude of the frequency response. And there is an interesting thing is it's 1 over tau, because you can think about how fast this decay to 0, and that will probably relate to how far away this omega is from this point, right? And that distance is 1 over tau. So how fast, like how narrow your low pass filter is will depend on this number tau here, or more like 1 over tau. And we can also plug the angle, and you can see that when omega is around 0, the angle should be 0, and the omega goes to infinity, the angle should become negative pi over 2, and also decay at the point around 1 over tau. Any question about the first order system? No? Okay. Cool. And then we have second order system, and as you can see, it's second order because they have second order differentiation here. And we also pick all the constants here in this particular form because we already know this form will give you a nice answer. So we have some omega n here and 2c omega n here. And I think this is not totally general, but it's probably okay. So, oh, you can absorb out the interactions, yeah, that's fine. Yeah, so we have the coefficient here as omega n squared, and these are 2c omega n, and if x is something else, you will solve it into x. Okay. So anyway, that's the second order system, and you can similarly write down didn't, but yeah, you can write down the Fourier transform here. So we have done this many times. So you can read the Fourier transform here. So this is omega n squared go to this omega n squared, and every differential here give you j omega, so j omega squared, 2c omega, j omega, and omega n squared. And you can also write this as the Laplace transform. So when you write Laplace transform, all the j omega become s, so like this. And now it's second order, so you have two roots here. So write root number 1, root number 2. Okay. And ROC, I guess we didn't quite specify ROC, but we'll assume as ROC include imaginary axis. Okay. But anyway, so now things are a little more interesting. So there are two roots of those equations, and if you solve them carefully, the two roots look like this: minus c omega n minus c omega n plus omega n squared minus 1, omega n c squared minus 1. Okay, and I think we will assume omega n is positive. Yeah. Omega n should be a positive real number. Okay. Yeah, it can be negative or positive, but it's better to choose it positive because the convention is choose omega n positive, and everything should be real here. Okay. And if you have a negative sign here, it's really a different system, and the second order system we have a positive sign here. Okay. Anyway, omega n is positive, and you have two roots, and look at this, and their property will depend on c. Okay, and so you can really see this term here now. C is I think C is also C can be just real. C can be probably negative, but we don't consider here. Okay. So anyway, so since that C is also positive, but there is a weird point in C that is 1. So with the different behavior of those two poles when C is bigger than 1 or less than 1. So if C is bigger than 1, then both of those square roots are positive real. And if you plot those two poles, and they will look like this. There are some two real poles, and the middle is minus c omega n, but they are all going to be negative, like this. And then back to the analysis we want to do here. So now we want to look at the Fourier transform of this thing. So you think about you move your omega around this j omega axis, and what are those two vectors look like. And once again, the vectors are going to be, well, the vectors, both of them are going to be smallest when your omega is 0. So okay, we observe this picture here once again. So both of them are going to be smallest when omega is around 0, and they're going to be decay. And the vector going larger, so that's why your response is going to be decaying. Okay, so that's the black line here, or the lower negative line here. Okay, and also we have some engineering example of the first order or second order system here. If this RC circuit is going to be a first order system, and if RLC circuit is going to be a second order system. And once again, the second order system can be looked at as low-pass filter. And okay, so that's a case where C is bigger than 1 or equal to 1. And also you can kind of see that the decay here will be controlled by the distance to this pole, and you can do some calculation. And I believe that's how you get this 1/2C here. But anyway, you can calculate it out. And that's the other example. So the other example is when when your C is less than 1, then you will get 2 complex roots. So do we have it wrong? Why we have these things? Oh, here. Yeah. So see, if your C is less than 1, then those 2 plus minus omega square root terms are imaginary. So you will have this minus C omega n and plus minus imaginary number. Okay. And so you have those two complex roots. And so when you work your omega from negative to infinity, then you will hit 2 points. One is here, when your omega is around here, and then the distance of this pole is very small, then you will get a strong response. And also if your omega, if you work up here, and your omega, and then your distance with this pole will be very small, and you will also get a strong response. So your response will look like this. It depends on how close to 0 your C is. So if C is okay, because the distance here also depends on C. So when your C is close to 0, then if your C is close to 0, then the spike around those points will get larger. Okay? And so here you see. So if your C is less than 1, then you will have 2 peaks around those 2 points. and C gets smaller and smaller, then your peak gets larger and larger. And that's also how we get. So if we give this log plot, and those are those spikes here. Okay, so the Q is 1 over C. Oh, sorry. So that's a different thing. Okay, so this Q is 1 over 2C, and we are seeing that when C gets smaller, this Q gets larger, and we get more spikes around those points. And you can also see that kind of as a property of the system, because if you don't have this term, then you have dy squared dt squared equal to omega plus omega 1 y squared equal to something. And if you don't have this thing here, you can see that sine omega nt and cosine omega nt is just a solution of these two terms. Okay, so this is oscillatory terms, oscillatory system, just basically the RIO circuit. Sorry, the LC circuit. There is a natural oscillation frequency in it, and the big spike here means that your system is in resonance. So this means that if your input, so your input X here, if it's in the natural frequency of the system, then you will get some resonance of your system with your input, and you will get a very strong response. That's why you get a spike here. And C basically controls the damping of your system. So if you have a very strong damping, then you never get this resonance response, but your damping is small enough, then you will get this spiking output here. And also you can analyze the angle of the response, which is the angle of the transfer function. Okay. And yeah, you can think about angle here, so you get there's 0 angle here, and yeah, it's not too fun. So yeah, that's a second order system, and I guess we'll see later that okay, so those are similar things. Also, I think one thing to say is you will see later that if C is negative, then the system is unstable. Okay, so that's something I missed. So C is negative and the system is unstable, so it's pretty bad for building a system, but sometimes you want that too. Anyway, that's that, and we can probably skip all this. And so, any question yet? Before we go to Laplace system, any question on the first order and the second order system? If you want to see the plot here, it's pretty easy. Just this qualitative, you can just look at the pole plot and then see how close you are to each pole. If you are close to some pole, then you'll probably get a strong response. Okay. Yeah, then Laplace system. It's what should I say? The concept is really easy. It's the system that has the magnitude not changing when you move your omega around this axis. And how can you have that? That is, you have some symmetry on this thing, right? So if you have like a symmetry between your zero and the poles, so you have whenever you have a pole, so for example this system, you have a pole here at the negative A, and then you have a 0 at this positive A. Then, no matter what your omega picking, when you calculate the system function, right? So you need to have this vector dividing this vector. The complex number of this vector dividing the complex number of this vector. So you will get some weird angle theta, but the good thing is the magnitude of those two vectors are the same. So no matter what omega you pick, the magnitude of the system function is always going to be 1 because it's left-right symmetry. Okay, and you can kind of imagine even if there are many poles and zeros, as long as they all have these symmetry pairs, you will have this magnitude being 1 through all over. Okay. And those kind of system, we call it Laplace system. Just whenever, whatever. So if a system that the response has a magnitude 1 through all the whole j omega axis, then it's called the Laplace system. And they need to have this symmetry on pole zero pair. Okay. And so the magnitude is going to be 1, and we can calculate the angle a little more carefully. So you can calculate the angle by just doing geometry. So because this triangle has this side equal to this side, so this is theta 2 and this is also theta 2. So we have theta 1 equal to pi minus theta 2, right? Just by geometry here. And and then you think about your system function, and it should be this vector dividing this vector, and then so the angle should be theta 1 minus theta 2. So, but theta 1 is pi minus theta 2, so the total angle is pi minus 2 theta 2. Okay. And yeah, so pi minus 2 theta 2, and if you also think a little more carefully, you can write theta 2 as the exact tangent of your omega and A. And excuse me. And yeah, then you can write everything algebraically this way. And okay, yeah. And then you can draw a picture here, like this. And I guess so you can see the magnitude of the system function as we set is a constant 1 for omega, and the angle has this decay, and so one thing to say is this discontinuity here is fake. It's just because how we choose arctangent. So I guess you want to think about it, it's more like you're starting with 2 pi and the function goes down and it goes like this. Because there's, if you think about angle here, there's really no discontinuity. It's just because we want to cut our arctangent at this point. Okay. The angle should go pretty smooth. Okay. Any question about what's the Laplace system? So the signature of Laplace system is that when you draw the magnitude of this h, then it's 1 everywhere. Every 10 more minutes. Okay. Anyway, that's Laplace system. And we see all the picture here once again. And so that give you started about how you think about the poles and zeros of the Laplace transform and the meaning to Fourier transform. And now let's go to this section. We see this section for every transform, so properties of Laplace transform. And as you expected, they are very similar to the properties of Fourier transform. And but the different part is now every Laplace transform has a ROC, and when you apply those properties, you need to think about what they do to the ROC. So the first one is the property that we have implicitly used many times. That is when you add two signals together, then the Laplace transform will be adding together, but the ROC should be the union of the ROC of those two. Okay? Although there might be some weird case, but we pretend they don't exist. Okay? When they cancel each other. In general, we will have this. And also it's a linear combination, so you can multiply a number. You can probably infer from here that when you just multiply your signal by a number, then ROC doesn't change. I guess unless the number is 0. But we kind of ignore the degenerate case. So anyway, let's say everything once again. So have signal number 1, and it has a Laplace transform with ROC number 1. And signal number 2 has a Laplace transform with ROC number 2. Then you have a linear combination of those two signals, so x1 plus bx2. Then the Laplace transform is also going to be linear combination, just like in all the Fourier transforms. So a big x1 plus b big x2. But now the ROC is going to be the union of R1 and R2. And you need to be union because you want both x1 and x2 being convergent on this region. Okay, so we need both of them, the end relations. So we need both of them to be convergent on here, and that's why you have a union. And we have seen this many times in the partial fraction expansion things. Question? No. Okay. Then we see this once again. Okay, so let's read through this. So we have the Laplace transform. Okay, is this the degenerate example? So we want to have the Laplace transform of this x over t. Okay, so we say it's the union here. Okay. So we are actually technically correct that we say it's going to be a union, but we We don't say it's quite a union, we say it's containing a union. Okay, so it can be a little bigger than a union if you are lucky when things are canceling out. Okay, so this is the example of you getting exactly cancellation. Okay, so anyway, so it's going to be set up really like this. So your signal is going to be some x1 minus some signal x2. So a linear combination is a equal to 1, b equal to minus 1. And the first Laplace transform, the Laplace transform of the first signal is going to be this x1 of s, and it's one way, so it's a pole at -1, and RC is the bigger than -1, and x2 is one way, x2 is plus 1 and s plus 2, and RC is also bigger than -1. And then we take the difference of those things. Then you found out that because it is set up really nicely, then do the calculation, then you see it's actually just 1 raised plus 2. So basically the -1 pole here and the -1 pole here cancel each other. So you only get a -2 pole here. Okay. And now you're thinking about the ROC of this thing. Okay. So if you take the union of those two ROC, it's RES bigger than -1. But that cannot be the ROC of these two, because this thing don't have the pole at -1, it's already cancelled out. And it's a rational function, we say the rational function ROC must be bounded at all the poles. So yeah, so that's because the divergence at -1 cancels out. So the ROC is actually going to extend to -2 here. Okay. And yeah, so that's one of the weird example where the ROC is bigger than the union because some singularity cancels out. Okay. So here are the picture of this example. So the first Laplace transform has the pole at -1, and the ROC is this positive part. And the second function has a -2 pole and a -1 pole, and the ROC is also this positive part. And when you take the difference of them, this -1 pole happens to cancel out, and you are left with this -2 pole. And the union of the ROC of those two should be from here, but it's a rational function. The ROC cannot really be contained by nothing, so extend it to this -2 pole. Okay. And yeah. Any question? If not, we have 2 minutes. Maybe we can go through a little more. Okay, and we can do time shifting property. So once again, this is really similar to the Fourier transform, and the derivation is the same. You can look at the, I guess the synthesis. Anyway, one of the two formulas of the Laplace transform. Yeah, probably the analysis relation. Okay. Anyway, you can look at the Laplace transform formula and do this change of variable, and you will get this HR e to the minus t when you change t to a minus t0. And ROC doesn't really change because this thing is basically, you can think about this thing give you HR divergence, and the answer is no, it's pretty divergent, pretty it's the finite value for any infinite, so it's okay. And then you do a shifting in the S domain, and it's different, a little different. So it's very symmetric to this. So you shift S to S minus 0, and you can do Hausen calculation, and you found out you will get HR e to the S not 0 here. But now the ROC will change, and it's not really surprising. You are basically doing a shifting in S plane. So everything in S plane will get shifted, and the ROC will also get shifted by this S0. Okay. And yeah, you can kind of see this in a picture. So say you have some LC of your original signal here, and now so you have some pole at A, and you see that when you change the function to s minus a0, then your pole will get shift to s minus a0. So the pole shifted, so the LC will also get shifted as well. Okay, and okay, exactly on time. So if there is no question, we'll have a break now, and we'll continue next class. Continue in 10 minutes. Okay. I think time to get back where we were. Yeah. So we have the time shift. So the shift in time domain and the shift in the frequency in the S domain. And we'll get this exponential. So remember in the in the Fourier transform, you will get j omega t and j omega ss, so you get st, and similar, or more like minus j omega, and plus j omega becomes s. Okay. And the more interesting thing here is now your RLC will get shifted when you shift in the S domain. And also, special case here is it's a case where the RLC doesn't get shifted. So, but you can go back to the the Fourier transform case where you kind of shift with the purely imaginary thing. And yeah. So anyway, so if you shift your s with j omega naught, it basically means your x is get multiplied by, then your x of t will get multiplied by some into j omega naught t, and this multiplication is modulation. It can be also seen as modulation. Yeah. Okay. And in this case, because your shift has no real part, then this addition is not changed. You can think about your shift everything in the y-axis, then because your RC is a strip, so it doesn't change your RC. But all your poles and the zeros will get shifted up or down by this j omega naught. Okay, any question? Not. Then let's see, the next one is the time scaling. So, okay, now everything is continuous, so you can shift with any continuous number. So time scaling x of at, then it's also similar to the Fourier transform formula. So get this 1 over absolute value of a, and s gets shifted to 1 over a. So yeah, just like Fourier transform, you have a stretch in the time domain, and you're compressing the frequency domain or S domain here. And also if you have a compressing time domain, you get stretching in S domain. And structural compression will also change your ROC. So yeah. So your ROC will become a times the original ROC. Okay. It might stretch or compress your ROC depending on whether A is bigger than 1 or less than 1. And also A is a real number here because time we still think as a real number, so we don't have imaginary time. But we have imaginary frequency. Okay. And anyway, as a special case, if you do time reversal, so just plug in A as a -1, then it's 1, and you get -1, so you get also negative in your frequency, and your ROC will get a negative sign. And that's like turning your no, ROC is up down, yeah. So it's like flip your ROC left and right because it's a strip. Okay, and we have some example here. So we have some example of this ROC equal to A times R. So you have the original signal with ROC on some R1 and R2. And then we have an example where A is less than 1. And so that's stretching the time domain and compressing the frequency domain. And anyway, so yeah, so A is less than 1, then yeah, the compression in the frequency domain, and the boundary value here should get compressed, and it's multiplied by a number less than 1, so you get compressed. Okay, so that's nice. And also another example where A is less than 1, but its magnitude is still less than -1. So it's still compressed. Oh, sorry. Wait. Sorry. It's yeah, it's less than 1, but the negative magnitude is still small. Although drawing is a little weird, so it's kind of doing the compression first and then flip that and right. Although the compression here is not very obvious. But anyway, you can see the R1 become AR1 here, and this R2 become AR2 on the other side. So flip and left and right, and do compression or stretching, be dependent on this side. Okay. Question about the time scaling. No. Then let's do another conjugation. And yeah, it's still quite similar. So you do conjugation in X, then you get conjugation in big X. And so before we had that, when you get a frequency, you get a negation in frequency, right? So negation in frequency is basically, now we think about S, then that's changing, get a negative sign on the imaginary part of S, and yeah, so that's conjugation on S. Okay. And ROC should also get the conjugation on ROC, but ROC are strips, so it's already symmetric on the y direction. So if you do conjugation on the change, so ROC is just back to the original ROC. Okay. And once again, so that's what happens. You do conjugation. So both the function value get conjugation and the S you get the conjugation corresponding. Yeah. So this conjugation is like adding negative sign in your frequency. And also then we can think about what happens real. So real means this number equal to this number. So equal S equal to X star of A star. And once again, we can think about this in, I guess, we should write it here, so let me write quickly. So probably easier to think is, you can think you move conjugation on this side, so X star of S. Does this help? And little. Okay, let me write this down and see if this helps. So we can obviously move this, move the star to this side, but conjugate both sides. So X star of S equal to X of X star. Okay. And what does this mean? This means that all the poles and the zeros need to be complex conjugation pairs. Okay, yeah, sorry. And yeah, so here are some examples. So let's see, how do I? The reasoning is here. So if it's real, then we have these equations. Then if X of S has a pole as S naught, means X of S is infinity. Then okay, I think it works this way. So X of S is unbounded. Then X star of S is also unbounded because they do complex conjugation. It's also complex conjugation doesn't remove divergence, right? So basically X over, so if you do complex conjugation with infinity, it's still infinity. So x of s is infinity, x star of x is infinity. Then that means x of x star is infinity. Okay, so this means that if x is real, then x over s is infinity, then x over s star is also infinity. And the same argument can go through. So if x over s is 0, then you do complex conjugation, it's still 0. And that means x over s star is 0. Okay? So whenever you have a pole or a 0 at s, you will have a pole or 0 at x star. So all the pole and the zeros should be the complex conjugation pairs. So for example, those are two examples we solved. So if this real function and its distant function look like this, and its pole and the zero look like this, they are all in the real line, so it's a complex conjugation with itself. Or we have another example here, so this example with some cosine, and the transfer function look like this. And here we have some complex roots and zeros, and you see that they have pairs. They are in pairs. Okay. Any question on the conjugation property? So we get this, and now we also know a little more about the pole and zeros. So if it's real, then the pole and the zeros need to be these complex conjugation pairs. And it's something you should probably remember. Okay. Yeah, I think this is something you will get tested on. And it's a nice property to remember. Okay, then let's see the next. The convolution property. And basically looks like once again look at same as the Fourier transform. So you have a convolution with a two signal and you do Laplace transform. Then you will get the multiplication of the Laplace transform. And once again, the ROC is the union of the two ROC, but it might get extended, so we have the word containing here. And it's containing because you might cancel the singularity by being very lucky. So we have two examples. We have a very nicely set up example here. So the first Laplace transform is x plus 1 over x plus 2, and the second one is x plus 2 over x plus 1, and they all have a pole. But when you multiply them together, it becomes 1, and it's no pole, so the ROC need to be everything. And that's bigger than the union of those two ROC. Any question? No. Okay. Then we have differentiation, and it's also very similar. So you differentiation on the time domain, then you get the extra s in the s domain, and you can derive this by differentiating it's the inverse Laplace transform, so it's basically the synthesis equation for Laplace transform. Anyway, you do the derivation in time here, then you see the only CT penalty here is e to st, so you get the extra s. And similarly, you can do the differentiation in the s domain by differentiating the analysis relation. So basically, defining equation for Laplace transform, and you do differentiation of s on both sides, and only this depends on s, so we get a negative t. Negative tx is the Laplace transform of the big X ds. And okay, so this thing, it says the ROC is containing up. So this thing might make your ROC a little bigger because this S might cancel a pole at 0. Okay? And this thing doesn't have a chance to cancel ROC by doing different. sorry, it doesn't have a chance to cancel a pole by doing differentiation. So our C is the same. Okay. Question about the differentiation property in tan and ace domain? No. Okay, then let's see an example. Okay, so yeah, this is something we keep doing. So we know the Laplace transform of this exponential decay, and now we have extra t in front. So basically, we want to get some polynomial in front, and we want to see what's the corresponding Laplace transform, and then we'll use the differential property to get those extra t. And so this is how it goes. So we start with this known equation. So e to the minus ATUT. Laplace transform gets to 1 over s plus a without c that's bigger than negative a. Then we apply this thing. So we get differentiation of s on the s domain, and then we'll get a negative t on the time domain, and we put a negative sign here, okay, because we don't want negative sign here. And you do the differentiation, and find it's 1 over s plus a squared. Okay? And the RC doesn't change. Question? So yeah, that's how you pull down extra t in front of your function here. And similarly, if you want extra s here, you can do differentiation with t on this side. And yeah, and you can also get even more power of t by doing more differentiation. So if you do differentiation once again, and I believe it will get some 2 here, so and then move things around. So if you differentiation with 2 here, then you get a 2 here, and then move a 2 on this side, so you get 2 here. And you can keep doing this, and you'll find out that you get t to the t minus 1, sorry, t to the n minus 1, and divide by some n minus 1 factorial here. And you get this nice formula. So this formula is, as you can probably guess, is useful on both sides. So first you can think as just what is this Laplace transform of decaying exponential and times a polynomial. Then you can use this formula to get your polynomial as the linear combination of monomials. And just look at this formula and write down its Laplace transform. Or the thing we'll probably get used more is when you do inverse Laplace transform. Remember, when you do partial fraction expansion and you have some root, some poles that is high order, then you cannot do partial fraction expansion. But now we know that for the poles with high order, what's the inverse Laplace transform is you look at this table. So it's an nth order pole, then it becomes exponential with t to the minus 1, also divided by this factorial. Question? Okay, not? Yeah, so this is a derivation of some formula that you will keep pulling out when you do the inverse Laplace transform of the rational functions. And okay, then we see the example of using it immediately. So now this is the example of Laplace transform of this whole thing. It's a quite complicated rational function, and if some polynomial here and divide by, okay, we already factored here for you, so that's nice. So you have 2 poles at a -1, a double pole at -1, and a pole at -2. Then you do partial fraction expansion, and excuse me. Yeah, and well, the first thing to check is that The order here is the order on the numerator is 2 and the denominator is 3, so you don't need to write down the extra quotient term, but you need to do partial fraction expansion. And now there are going to be 3 terms. So this one pole will get 1 term, and this double pole here will get 2 terms. So we'll get x plus 1 square term and x plus 1 square term. And now how to get an upper number here is, I think that's one trick, but anyway, if you just expand everything out, then you can solve the 3 by 3 linear equation. So that's doable. And we already do skip the solving here, and we got the coefficient 2 minus 1 and 3. Those 3 things. And okay, so we are okay, yeah, and here we are in a lucky region, right? Because for this thing we haven't talked about what happened when RC is the other side. But anyway, so we are in a region we know. So we have the ROC that on the right side of everything, okay, or the -2 and the -1 pole. So we are inverting all 3 of them to the right-sided function. And so this thing inverted to right-sided function is exponential decay times ut. So everything right-sided, so they will have is ut. And so those 2 we know from the example long time ago. So 2 get 2, 1 get 1, and then -1, -1, 3. And now this x plus 1 square term, we can use this example. And you see that this square give you the t here. Okay. Question from this example. And I'm not sure. Oh, and you can probably derive. So yeah, so you can probably do it as a homework exercise to derive this thing when the ROC is on the other side, right? Then the ROC is RES less than -a. Then you need to start with the ROC is on the other side and do differentiation from there. Okay. Question? No. Okay. Then let's see this a little weird example. So okay. So now differentiation, then we have integration. And integration in the time domain. Now differentiation give you s, so integration will guess that you get this 1 over s. And now you get the extra pole here. Okay? And the ROC will be so you get the extra pole at 0 here. And this 1 over s will be taking on the ROC of the positive side. So this 1 over s, we take it ROC being RES bigger than 0. And the ROC of the total thing need to be a union of the ROC of this thing and the ROC of this 1 over s. And but it's also thing containing because things may cancel each other. Okay. And we can derive this using the convolution property we talked about before. Okay. So it's how this work. How this work is that this integration from -infinity to t x of tau d tau can be think of as the can be think of as the convolution between u of t and x of t. Okay. You can work it out. Basically, this u of t, So when you do convolution, you take the integration from negative infinity to positive infinity, and this u of t will call the upper bound as t. Okay, so it's a really nice way to write things. And then we think about what's the Laplace transform of u of t. Well, Laplace transform of u of t is basically the Laplace transform of this little more of this, right? So if you just take a equal to 0, then this side is just u of t, and this side is 1 over s, and the ROC is RES bigger than 0. Okay, so the unit step function is the Laplace transform 1 over s, with the ROC picking the positive side. Okay, and then you just use the convolution property. So this side is a convolution of two things, then the other side is a multiplication of two things, so it's going to be x of s times 1 over s, and the ROC should be the union of the ROC of this thing and the ROC of this thing. Okay. Question? If you don't have question, then you should. Okay. And okay, but now this is a little weird. You think about it. If you try to compare, let me try to convince you here. So if you try to compare this to Fourier transform now, if you remember what's the Fourier transform of integration, now you see that you are missing something. When you do Fourier transform, when you do the integration on Fourier, when you do Fourier transform on integration, instead of this just 1 over j omega, you also get a weird delta term. Okay, so, and a very good example is you do union state function and you do Fourier transform is just 1 over j omega plus pi delta of omega. And yeah, I guess there is not too good of explanation here, but the one thing I can say here is that this is consistent with this thing, because so we have been saying that the Fourier transform is the Laplace transform restrict to the imaginary axis, right? So the Fourier transform should be this thing, plug in the s as j omega. But now this is a very weird thing, because j omega is actually not in the ROC of this thing. Okay? So yeah, the ROC is s bigger than 0. So s equal to 0 is actually not inside ROC. So the Fourier transform is not equal to ROC, that's why it can be this weird pi delta of omega here. But okay, yeah. So it's really weird, but both of those are true. And I guess one thing I can say is you can see they are still quite similar, because you have 1 s here and 1 over j omega here. But you do get this weird thing, this delta function basically sitting on the singularity. And yeah, that's just what it is. Any more question? And I guess so this weird thing happened. The unit state function is also why for Fourier transform the integration also has the weird delta function term, but for Laplace transform it doesn't, because the ROC doesn't contain this weird delta function. Okay. Okay, no question. Then okay, I should have pasted this in a previous page. Anyway, yeah, the derivation of this thing. Okay, so okay, so this is that. Then we Now start to talking about some property that's very weird, the property you haven't seen in Fourier transform. This is specific in Laplace transform, and we use this because we are going to use Laplace transform to do something very weird. We are going to use it to solve differential equation with boundary condition or initial condition, which is not very weird if you think about how you solve differential equation, but it's very weird if you think about the differential equation as a system, because differential equation with some initial value condition basically not LTI, and we are thinking about, we have been treating everything as LTI, but yeah, we are able to do it somehow with the weird version of Laplace transform later. And also this is the initial and final value theorem. And yeah. Guess we don't have too much intuitive here, but they are very useful. And anyway, so the two theorems. So first you need a very special condition here. And so you need to consider that your x of t is 0 for t less than 0. So the theorem for some function x of t and its relation you can see here to its Laplace transform big X of s. And so if you think about this system function, so basically your system function is causal. Okay, so x of t is 0 for t less than 0 means if it's h, then h of t for is 0 for h t less than 0 means your system is causal, right? Hopefully you still remember that. And anyway, so this x of t need to satisfy this, and you also need to behave nicely around this 0. So we have a sketch of your x of t, how your x of t should look like. So the x-axis, x-axis, and it needs to be 0 when t is less than 0, and it need to be kind of nice around this t equals to 0 line, so there's no weird impulse and other thing, but it's okay. But there is a little singularity here, so there is no delta function things that go to infinity, but x can be discontinuous here. Okay, and this is what we are interested in. So x will start 0 for every negative 10, but I can jump start at some value x of 0 plus here, and that's what we are trying to figure out. So what is the value of x of t when when you are approaching from this positive t side? So we are thinking x as this kind of function is should be pretty nice when t is bigger than 0, but it jumps up at. So you have a discontinuity here, you have finite discontinuity here, and x jump start at some value x of 0 plus. And so a really special thing about Laplace transform is that you can determine this x of 0 plus by calculating in Laplace transform and times x, then take x go to infinity. Okay, and yeah, I don't have too many intuition of this, but the derivation is in homework. So basically, you derive this by thinking the Laplace transform as using Laplace transform is basically always an analytical function, and you can do Taylor expansion, and you work out all the Taylor expansion coefficients, then you find out this is true. Yeah. And so this is something you need to remember because it's very useful in solving differential equation. And this is what it is. So limit x goes to infinity, x times big X of s is the x value, initial value of x at this 0 plus point. And also there is final value theorem. And it's kind of swap this 0 and the infinity here. So it says that, so we still need this causal condition. And I should have, let me draw here. Okay. So we still want x of t equals 0 when t equals 0. But now x of t has a finite limit as x goes to infinity. So basically you want this limit to exist. So now the function looks more like, so it still start with 0, and but we don't really care about jump here, so it's whatever. But if t goes to infinity, x approaches some value. Okay. Approach some value, so maybe going up and down, but it will converge to some value. And they want to see what's this value here. Then you can use, then you calculate basically the same thing. Still s times big X of s. And but now you take x equal to 0, and you get you the final point of x of t. Very cool, and it is true. You can, or you will do a derivation in your homework. It's problem 9.59. So I guess let's see how this works out. So maybe you'll get a little intuition on this. And for example, this thing. So we have x of t equal to, this is the previous example, so this exponential decay, then exponential decay times another cosine. Excuse me. And okay, yeah, and we have calculated a big X here, big X before, and so that's sin x squared and 5 sin x squared times 5 is plus 12 something, and then we can easily calculate. So it gives you some rational big X, and then we multiply it by some small x, and then we get this rational function here. So sin x cubed divided by sin x cubed. Okay, that's just multiplying out what we had before. And then we can check the initial value and the final value, right? So two things. So initial value, then you want to take x goes to infinity, and its rational function, so 2 polynomial when x goes to infinity. Then you are just looking at the highest order term, and so that's 2x squared divided by 2x cubed divided by x cubed, and so you just get 2 here. And now you can see if that's true from here, and that should be true, right? So this thing, when x go to 0 plus, so obviously they both satisfy our x cutoff t equal to 0 thing, because you have two unit step function here, and at time 0 plus, then you get 1 here. So when t equals 0, this is equal to 1, and t equals 0, this is also equal to 1. So we have 1 plus 1 equal to 2, and so you see that our initial value theorem works here. Okay. And okay, we have 10 more minutes, and let's see, can we also do final value theorem here? Yeah, I think we can do final value theorem here, right? So, but it's a little boring here. So final value theorem here, when t go to infinity, then you get exponential decay, so final value to be 0 here. And let's also check out by doing s go to 0 with this thing. And yeah, basically because you don't have a point s equal to 0 here. And so this thing, when you take s go to 0, then the denominator become 20 and the numerator become 0. So you have a 0 divided by 20, that's 0. So the final value theorem also works out here. More question about the initial value and the final value theorem. I think you kind of just need to remember them. They are really nice. So you have those functions, and I think it is pretty important. You need to satisfy the condition that x over t equals 0 when t less than 0. And when that's true, then you have this initial value theorem and the final value theorem. And also obviously, so this is a quite strong constraint, but if x over t look more like it started some random time, right? On t at t naught, then you can just time shift this t naught to 0 and then apply your theorem. Okay. Okay. Draw this a little better. I think it's probably good. We have 8 more minutes. Okay, so let's look at this table first. So the thing we talked about. I guess there is no possible relation here because the AC is whole domain. We don't just go through one line. But anyway, so the signal and the Laplace transform pair, and then now we have an extra color that we always need to look at ROC. And with linearity, the Laplace transform part is also linear, and the ROC is a union, but it is a list. And time shift, you get the extra e to the minus st t naught. And yeah, extra e to the minus st naught, and the ROC, and and then you have s shifting, then you get e to the s naught t, and ROC is shifted with this s naught. You need to shoot by real part of this s naught. And time scaling is similar, and ROC also scaled by this a. And when you do conjugation, then big X also conjugate, big X is conjugated, and S need to be S star here. And the ROC doesn't change. Convolution is then you get multiplication, and the ROC is a union, at least. And when you do differentiation, you get the extra S. And differentiate with s, then you get this negative t, and you do integration, then now there is no extra term, you just get 1 over s. And ROC will get smaller because you need to take into account the ROC of this 1 over s, which is 0s bigger than 0. And then we have this really two new theorem, the initial value and the final value theorem. Says that if you want to find the initial, so you have a function that's function that's 0 for t less than 0, and you want to find the initial and the final value of it. And so the initial and the final it should behave nice, so no weird impulse at initial, and actually has a final limit at infinity. Then the initial value is limit x goes to infinity, x times big X over S. And the final value is x goes to 0, x times big X over S. Okay. 为什么体域积分的拉普拉斯转换跟佛列转换会有派 x0那项不同？就是我们解释，就是怎么说呢？因为它很奇怪，因为 Laplace Transform 我们只取比较好的部分嘛，就是我们刚刚讲的。例子给个例子的话，是像是这个 unit step function 嘛，unit step function 你有多这个奇怪的 delta function here，delta function 出来，但是 Laplace Transform 时候没有，因为 Laplace Transform 时候我们把奇怪的部分都割掉了，我们选的 regional convergence 是 s 大于0的，然后如果你想这样把这个要换回 Fourier Transform 的话，你只要选 purely imaginary axis 嘛。那 purely imaginary axis 代表 RES 等于0，所以这东西其实不在它的 regional convergence 里面。所以我们这样子解释它们不一样，但是算是只解释了为什么它们可以长得不一样，但是这个很奇怪的为什么出现delta部分，那就是 Fourier transform 的时候有一些奇怪的事情发生。但是 in general Laplace transform 都会长得比较漂亮一点。Laplace transform 比较少看到这些delta的东西。因为我们会把怪怪的东西都用 regional convergence 割掉这样子。OK。Does I need to answer your question? 对，基本上就是后面那个东西不在 regional convergence 里面。OK。Yeah. We have 3 minutes. We can probably look at this table and yeah. So some nice Laplace transform pairs. I think we have derived most of them, right? And so let's see. So delta function is Laplace transform 1. Okay. I don't think have we derived. We have talked about this. But the derivation is, well, you can just do the integration and you will get a Laplace transform 1. Same as the Fourier transform. You can also get from extending Fourier transform for 1 and a1. And 1 is convergent everywhere, and so ROC is everything. Then we get this unit step. The Laplace transform is 1 over S, and yeah, this is from the oh, we don't have that. Okay, this is from the here, right? So this is a special case of this first example we have the exponential decay with alpha. So we take alpha equal to 0, then you get unit step here. And also the other thing, we have this the left-sided exponential decay, and yeah, and we can also take alpha equal to 0, then you get this left-sided unit step with negative sign, and this Laplace transform is also 1 over S, but the ROC is being left-sided. And then you can do differentiation on those two 1 over S multiple times. Then when you do differentiation, you get some t here, so basically you get a polynomial here on either negative side or on either right side or left side. And anyway, so you have multiple topos at s equal to 0, and either positive ROC or negative ROC, then you get the inverse Laplace transform being those two polynomials cut off at t equals 0, either right or left. And then we have the 6 and 7, the first two examples we talked about. And then we can do also once again do differentiation on the S side, and then you get these multiple poles. So if you get a differential of this, and the ROC doesn't change, and you will get this equation. This is the example we run through today. So you get polynomial with t here. And yeah, so that's one way to passate one. And then if you want to invert this with the RC on the other side, then you need to do the differentiation of this thing on this side, and it's basically the same. You just get a negative sign, and because on the time domain you are just multiplying more t here. So yeah, it's the same. You just inherit this negative t here and the negative sign here. Okay. And then there's delta function shifted by some t, and you can do time shifting from here. So that's e to the minus st. And LC is still everything. Oh well, over time. So let's stop reading this. And yeah, you can see the other things yourself. Okay, any question?用拉普拉斯解微分方程比傅立叶好吗？应该说，这个有点奇怪的问题，看情况吗？可以解比较多东西啦。傅立叶可以解的情况比较少，基本上是傅立叶要解的话，基本上需要我们的那个 initial rest 嘛，所以我们考试的时候没有讲很清楚，就是傅立叶基本上你需要 initial rest condition， 写一下，然后那样的话会，对啊 ，initial rest， 然后也就是，或是换个方法讲的话，你需要是 causal LTI 的 system 这样子。所以傅立叶的局限性比较大，然后可是用 Laplace Transform 的话，可以解一些奇奇怪怪的东西。对，我们后面会看到，像是 initial value problem 啊 ，boundary value problem 之类的。或者是什么解出来，然后说它有 anti-causal 之类的。对了 ，Laplace 应该是可以通用比较多奇怪的东西。哦，希望是。OK， 那先这样停止。结束了。